Hey there, good morning, Algebra 3. Hopefully you've had a good weekend and you're looking forward to the nice break coming up. But this week we have to get some hard work accomplished. We're going to look today at the graphs of tangent and cotangent functions. You've been hopefully practicing really hard with the sine and the cosine, because once you understand basic sine and cosine graphs, the tangent, cotangent, and then the secant, cosecant, because you have a baseline of understanding, should be that much easier. So hopefully you've done a good job with those assignments and you're ready to go with this whole idea of tangent and cotangent. Now, what I want to remind you of is that when you are thinking of a tangent on a unit circle, okay, you're thinking of the y over x values. So for example, here you'd have 0 over 1, which would be 0. I'm going to skip this one and this one for a second, but if we look at pi over 4 real quick, you'd have this number over itself, so that would give you a 1, and that's going to turn out to be significant and important. And another thing that's important, when you take y over x in this location, you get a number over 0, which means that you have an undefined value. And that's going to be super important in our understanding. Okay, the other values, of course, are taken by doing y over x, so you could look at pi over 3. Okay, as the values are getting further and further along here, okay, what we are going to find is that those numbers get to be greater and greater and greater when you compare y to x, because the x's are going to be getting smaller and the y's are going to be getting greater, so the number will be getting greater. So I want to take a look at that when we take a look and we make a list of ordered pairs. So like I said, when we started at 0, you ended up with 0 over 1. You ended up with 0 over 1, which gives you 0. When you looked at pi over 4, we had a number over itself. I do want you to, kind of, I know you can think it through, but when we do something like pi over 3, we get square root of 3 over 2 divided by a half. That would give you square root 3. Or when we take that, we would be able to get a number. You can put it right in the calculator if you want, get an approximate value. And so what we find out for is that at square root of 3, we get 1.7, which is at pi over 3. Pi over 2 is a whole different thing, as I said, and that's where we get our undefined value, because y over x, number over 0, gives you undefined. Okay, well, that's all interesting. And in terms of when you want to turn this thing into a graph, we have our x and we have our y, which is different than our x and y values in our unit circle that we use to find these numbers. Okay, so what we've done is we found that there is a place where there is no value. And as I was trying to explain, as we get closer and closer to that value, the number is going to be getting higher and higher and higher, but it's never going to reach that undefined value. Now, what about these negatives here? Okay, when you think about negatives on the unit circle, what we're thinking about is going backwards. So negative pi over 4 takes us to here. Okay, so negative pi over 4 would end up giving us a negative 1. Okay, a negative of a number over itself gives you negative 1. If we go to a negative a third pi, you're going to get that negative 1.7, because you'll be taking this number over this number, which would reduce down, and take it a little bit further in the negative direction, going backwards on the circle, and we get another undefined. And those undefineds are going to be super, super important when we're trying to figure out what our graph looks like. Okay, so back to here. Okay, we have -1 is at negative pi over 4, and we have this. So you kind of see bookends sort of as a repeating pattern, just like we had in sine and cosine. You had something and you had a pattern repeating. But what we need to think about is also where the tangent is going to be undefined. Okay, the most important part when you do sine and cosine is figuring out where the zeros are. In other words, like where those nodes are along, where it's like snaking back and forth over it. The most important part on a tangent or a cotangent graph is going to be figuring out where the graph is going to be undefined. And when we think about it on the unit circle, just back to here, and you're thinking about these values as being y over x, the places where the x value is 0 is at pi over 2 and 3 pi over 2. And then if you go around again, you end up with 5 pi over 2 and 7 pi over 2 and 11 pi over 2, and cycling on and on and on. If you're considering negatives, you go to negative pi over 2 this way. So all those different values are going to give you undefined, and those are important when we're dealing with a cotangent or a tangent function, tangent in this case. So where else they're undefined would be at negative pi over 2 and 3 pi over 2 and 5 pi over 2, 7 pi over 2, all of the odd pi over 2s. Okay, the even pi over 2s would end up being on the right and the left of the circle, so that doesn't work. So what we're bringing into this is that whenever you have undefined, that means there can't be a value there. And in the case of tangent, what we have is asymptotes that end up being there. So these are asymptotes, or values where the graph is going to approach it but not cross over it. And our basic important thing is to find where the asymptotes are. Now, an interesting thing about a tangent function is that the length of the period is not 2 pi like before. The length of the period is just 1 pi. And the standard initial 1 period gap goes from negative pi over 2 to pi over 2. So all that stuff that we did with sine and cosine, where you had the standard period being from 0 to 2 pi, that does not apply for tangent and cotangent. Okay? Tangent is a little bit different than cotangent, actually. Tangent will go from negative pi over 2 to pi over 2. So we want to look at that first as far as our values go. So if I just plug in these values that I have calculated here, notice that at 0 we have 0. That's going to be the easiest point to plot. At pi over 4, which is halfway through, that's where we get 1, and negative pi over 2 is where we get -1. When you're doing graphs and I grade them, okay, I'm going to be specifically looking for where you place your middle point and where you place these 2 points, the ones that would be at 1 or -1, or if it's a compression or a stretch, the ones that are to the right and the left. So I'm specifically going to be looking for asymptotes, and I'm going to be looking for 3 key points, and then the sketched in graph that goes with it. So just for the sake of showing one to start with, if we put in our 1.7, which would be about here, and our -1.7 right about here, what we have is a basic idea, and as we get closer to pi over 2, it's going up and up and up and up, and as we get closer to negative pi over 2, it's going down and down and down and down. And we find that our graph looks something like this. Please be careful that you're not drawing it so that your graph becomes completely linear. I know that sometimes it's a little difficult to get the little curve in there, but you know, make it as best as you can. It's going from down to up, and it's encased between asymptotes. Okay, so it's going from down to up. In case between asymptotes, I'm going to be looking for the middle point and then the halfway between the middles. Just like those were important points in sine and cosine, those points are going to be important. This pi over 3 and the negative pi over 3, I'm not specifically going to be looking for them, but I just wanted to show you a single period with a little bit more detail to start with. Okay, so you're getting the idea of where these things come from. If we want to extend it to 2 periods, okay, what you need to do is you need to go to the next asymptote. Our next asymptote is 3 pi over 2. What we notice is that our gaps were going from 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. Just like when we did with sine and cosine, if you can figure out the length of one of the gaps for the key points, you just keep on going at a nice even interval to get your second period. Your asymptotes are super important. Okay, your asymptotes are kind of like in our sine and cosine, like our beginning and our end point, but in tangents, those are where the asymptotes fall. Okay, so let's get down some facts that you need to write down about your tangent function. Okay, first of all, the graph is discontinuous. Discontinuous meaning that you would have to pick up your pencil to go to the next part of your tangent function. Usually if you draw them, you'd start with this middle point and go up and then go down. It just makes it easier to draw. But it's not like a sine curve that you can keep on going and keep on going and keep on going. It's discontinuous, meaning that there's gaps. Okay? The asymptotes are at the odd multiples of pi over 2. Okay, I had already said that, but just so you know that if you wanted to draw a million of them, you just have to go to the odd multiples of pi over 2. The x-intercepts are at multiples of pi. So 0 and pi and 2 pi and 3 pi and 4 pi. The period has a length of just 1 pi. It happens to go from negative pi over 2 to pi over 2. We can't really consider an amplitude because there's no maximum, there's no minimum, so there's not a top or a bottom. However, the idea of amplitude actually comes into play as far as where these points are that I'll be looking for, where the 1 and the negative 1 belongs, or if it gets stretched out or if it gets compressed, it might be closer or further away from the x-axis, but we don't technically have an amplitude for the tangent or the cotangent function. Okay, tangent and cotangent are very, very closely related. So I want you to have in your mind this part of your tangent function. This is your standard. Okay? Asymptotes at negative pi over 2 and pi over 2, starts down at negative 1, goes through 0, up through 1, negative 1, 0, 1, in that pattern to make that type of a graph. So that's going to be what you base all of your shifted graphs on. So you need to make sure you're very settled as far as what that looks like. Okay? Let's consider a cotangent, a regular parent function for a cotangent function. Now for a cotangent, you have x over y. So we consider a cotangent function being very, very, very similar to a tangent, because once again it uses those x and y points, but our asymptotes here where y equals 0 rather than where x equals 0. So here's where y equals 0, here's where y equals 0 also. A little bit even easier to think about a cotangent than a tangent. So at 0 and pi and 2 pi and 3 pi, 4 pi, and on and on and on around this unit circle, you're going to have an asymptote where y equals 0. Thinking about the other small points that we have here, you're going to have your 0 values at the odd multiples of pi over 2. you're still going to have a repeat happening with just half the circle, because when you do x over y, you're going to have, here you're going to get positive 1, here you're going to get negative 1. Okay, but the asymptotes are different places, so it makes those graphs look different. Okay, so let's take a look at what I mean by that. So when you take a look at your table here, our undefined values, like we said, were at 0 and at pi. Pi over 4 was at 1, and 3 pi over 4 is at negative 1. So our asymptotes here are in different places. Our asymptotes at 0 and pi, now when it's on an axis it's hard to see it, but it is here. Pi over 4 is giving you a positive. We keep going to 3 pi over 4 and we get a negative. So what we have is, instead of having a graph that's going up, like for a tangent function, we have a graph that's going down for the cotangent function. Okay, so our basic one period for a cotangent is from 0 to pi, and it's sliding down like this in a curved pattern. There's actually a bit of a curve that goes in here. It's just really hard to draw in very accurately, but I do want you to make sure that you have your 0, you have the 1, and you have the negative 1, or a variation on that when we have stretches or compressions. Okay, also it's discontinuous. Also, the x-intercepts are important. They happen to be at the odd multiples of pi over 2. And a period is also pi in length. But you do have to be a little bit more careful when you're setting things up, finding the beginning and the end of a single period. Make sure that you are consciously aware of whether you're dealing with tangent or whether you're dealing with cotangent. Sine and cosine were a little bit easier because you were always using 0 to 2 pi. For these, you have to be very careful which one you're using. So let's jump into a couple of examples. So if I want to graph y equals the tangent of 2x, first of all, you need to have in your mind that this is the one that's going to start down and move up. We need to use this part to find our asymptotes. Our asymptotes are important, as well as directly, completely in the dead center between them, and then also the quarter marks, just like we did, same process that we did with the sine and cosine. So you start with putting whatever's here between the beginning and the end of a standard period. Here's the beginning of a standard period, here's the end of the standard period, and whatever you're finding the tangent of has to go right smack dab in the middle. So you've got to get this x by itself. You could say divide by 2, but since it's by fractions, it's a little bit easier to think of it as multiplying each one by times a half. Because when I do times a half, this cancels out. Times a half gives me a quarter here and a quarter here. Those are where your asymptotes live. So when you're first starting out a graph, you figure out where the asymptotes live, and you draw them in. Once you figure out where the asymptotes is, you have to figure out where 0 lives. Now this one's pretty obvious as far as where 0 lives, because it does show up just right on the axis, but you have to realize sometimes, especially if we have a plus or a minus out here that you're applying the tangent to, you could have it shifting right or left, so you really have to identify where that 0 is. So in this one it's easy because you add these two and divide by 2 and it gives you the middle one, which in this case is 0, but I didn't want to skip that direction because we're doing more with it shortly. So you add the beginning and the end, divide by 2. This is where 0 lives in a tangent function. When you graph a cotangent function, it'll be the same process, you just have a different beginning and end of a standard period. So we plug in and plot our 0. There it is. After that, we need to figure out where our 1 and our -1 point go. So we do the same thing you did before, is add these two and divide by 2. Add these two and divide by 2. Just remember, dividing by 2 is the same as multiplying times a half. This is a y, by the way. It doesn't look much like a y. This is where y equals 0. All right. Whatever y, yeah, where y equals 0 because it's a 0 here, but it's also where x equals, where y equals 0, which gives you your x-intercept. Okay. All right, so let's find our middle points. The middle points are where y equals -1 and where y equals +1. Okay, so once again, not an amplitude per se, but very similar to it. That -1 and that 1 are important because it gives the shape and the structure to your graph. Okay, so here's where y equals 0. Here's where y equals -1, and here's where y equals +1. So you sketch in your graph, and this is a very nice tangent function. I will be looking for the asymptotes, and I will be looking for the -1 and the +1 value. I will be looking for the asymptotes. I will be looking for where one point and the other point and where 0 belongs. So please, please, please make sure that you're showing all of the key important parts of your tangent graph and of your cotangent graph. Okay, so super important there. Let's look at this other one. Okay, this one has a little bit more to it. We have this -3 to deal with. It's the same thing as in other cases. Our -3 is going to flip that thing over. It's going to make it upside down from its normal looking graph. It's also going to stretch it out, so we need to deal with all of those things. But first thing we want to do is we want to find out where our actual asymptotes are before we even do anything else. Okay, I have quite a bit that's going to show up here. We'll break it down. Okay, we need to show where our asymptotes are. This part right here tells us that it's going to stretch out. Okay, I can't say that the amplitude changed, but since it's multiplying times 3, those 1s are going to get stretched out to be 3s. Instead of being 1 away from the center, it's going to be 3 away and -3 away. We're going to flip it over also. This negative means that it turns over and goes to the opposite of where it would be. Remember, our standard normal tangent is going from down to up. Okay? But when you need to flip that thing over, it's going to be going from up to down, because you're taking your standard tangent that goes from down to up, and we're going to be flipping it over so that it goes up to down. Yeah, I gave you a glimpse, but I covered it back up on purpose, because we have to figure out where the beginning and end lie. So we start with a regular tangent function goes from -π/2 to π/2. A half x in the middle, so we need to multiply everything by 2. And when we multiply everything by 2, x is left by itself in the middle, and we get our asymptotes at -π and π. We need to then do our calculations to figure out where those other pieces are. And you remember from the others, you'd have to add these two and divide by 2 to get this one. 0 plus -π times a half gives you a half, -1/2. 0 plus 1 times a half gives you a half. This is where 3 lives. This is where 0 lives. This is where -3 lives. And these are going to be your asymptotes. Remember, normally it would start with a tangent going down to up, but this negative flips it around, so it's going up to down. Now my curve is not necessarily the best the way I drew it. It should be a little curvier. But I'm looking for your asymptotes. I'm looking for this 0 point, and I'm looking for specifically these 2 points, and then your best of drawing this to make sure that it's not crossing over these. I will make sure that it doesn't cross over these. If it crosses the asymptotes, I'll take off a little bit. If you don't have these 3 points, I'll take off some. You've got to make sure that your graph is like that. If it was a second period, you could say, okay, this is going by pi over 2s, so you would continue and you would extend it on. All right, let's hit another one. A half of a cotangent. Now a cotangent, remember, is a little bit different. A cotangent goes, the beginning part goes from 0 and the end part goes to pi. And a cotangent normally would go from up to down. There's not a negative, so we're thinking cotangent. We're going up to down in the range of 0 to pi. This half, though, means it's going to be smushed. It's going to be compressed, and we're going to be able to figure out how much as we go with this. So I've got to get 0 to pi. I divide everything by 2, or multiply by a half, so I find out that one complete period goes from 0 to pi over 2, and that's where my asymptotes live. Okay, I'm going to just do a quick sketch here. I've got on this, I'm going to go from 0 to pi over 2. Zero. I'm going to give myself a pi over 2 here. And that's where my asymptotes live. The other asymptote lives here. You can't really see it along here, but that's okay. We need to find our middle part. Okay, so 0 plus pi over 2 times a half. I'm finding, get rid of this. I'm finding 0 plus pi over 2 times a half. So that gives me pi over 4 in the middle. So I've got 0, pi over 2, and pi over 4 in the middle. That's where my 0 goes. Now we're looking at cotangent for this one. And cotangent, remember, starts up and goes down. Our normal one would be from 1 to -1, starting up and going down. But since we're looking at the cotangent at 1/2 the cotangent of 2x, I believe that was the problem. Yes, 1/2 the cotangent of 2x. What that means is that instead of going up to 1 and down to -1, we're going to go start up at 1/2 for y and go to -1/2. I do have to figure out this. And so when I add 0 plus pi over 4 times 1/2, I get 1/8. So pi over 8. And then this one, pi over 4 plus pi over 2 times 1/2. Okay, so pi over 4 plus 2 pi over 4 gives 3 pi over 4 times 1/2. 3 pi over 4 times 1/2 is 3 pi over 8. And then, so these are the values that go with these. These are your asymptotes. Okay, so we're starting at 1/2. Here's 1/2. Going down to -1/2. Remember I said I'm going to be looking for these key points. So I've got 1/2. and then I've got negative a half. This goes up like this, and then this curves down like this. And then you've actually seen it drawn, which should be helpful to you. This is what it looks like. So what happened is it got compressed. Our key points are here and here now. Pi over 4 is an important point. I'll be looking for all those things. And so you're going from 0 to pi over 2. Those are your key areas that I'll be looking for. Okay. I'm just going to run through a little bit more with you. Let's do 2 plus tangent x. All right, well, there's nothing going on here. It's a standard period for this one. It's negative pi over 2 to pi over 2. So nothing crazy. This is just your standard normal one, but the 2 outside here means the whole thing gets shifted up 2. So it looks like this. Okay, here's your value. Here are the normal values that we need to show for a tangent. Tangent does go down to up. But what happened because of this 2 means that my 0 point got moved up to a 2. My negative pi over 4 point, instead of being down here at negative 1, got moved up to be right here. And then this one had to be moved up 2. So just like where we had in the sine and cosine, we moved up the whole baseline thing so that it could pivot around that. The tangent also can have the whole thing dragged up. All right, and that goes along with some things you've had in your earlier algebras with other functions too, where you've got the thing out here moves it up or down, the thing in here moves it left or right. Here is stretch or compress, and that works the same way. Okay. All right, let's get one more that's a little crazy. This one's got about everything in it. This minus 2, think about it ahead and see if you can anticipate what it means. This minus 2 means down 2. A regular cotangent function goes from up to down, but this flips it over, so it'll be down to up. This part has to get put between, it's cotangent, so it gets put between 0 and pi. Down 2, upside down. This goes between 0 and pi. In order to make this work, I need to add pi over 4 to all 3 places. If you're checking on your calculator, you're doing here 0 plus pi over 4. That's pretty obvious. But 1 plus 1/4 gives you 5/4. Okay, so we've got our asymptotes. You need to figure out your middle. This is a little bit different. You need to figure out your middle by pi over 4 plus 5 pi over 4 gives you 6 pi over 4. But times a half gives you 3 pi over 4 for your middle. Okay, we'll show this just right quick. 3 pi over 4 for your middle. Okay. Then here you need to add pi over 4 plus 3 pi over 4, which is 4 pi over 4, and half of that is a half pi. 3 pi over 4 and 5 pi over 4 is 8 pi over 4, which is 2, and half of that is 1 pi. The whole thing moved down 2, so that means that my asymptotes go here on the end. The middle point is not at 0 anymore. It shifted down 2. My normal cotangent function would go up to down, but I have to flip that over, so I'm going down to up. So I'm starting 1 below. I'm going 1 below where my starting point is and 1 above where my starting point is. These two probably are things that you would find more along the lines. They're easier once you're actually going on the graph. When I'm doing a cotangent or a tangent graph, usually what I'll do is I'll throw in the asymptotes. Once the asymptotes are placed, put in my anchor point where 0 would be. And so if it moved down, do that. Take a look at what the shape is, keeping in mind that a normal cotangent goes down, up to down. It got flipped, so instead of starting up 1 from there and going down, I'm starting down 1 from there and going up. So I'll be looking for the asymptotes, I'll be looking for this center point, and I'll be looking for the two that are at the halfway marks. All right, I hope that made a whole lot of sense to you. This will be our last new lesson before we have our nice long Easter break. And so we will be having a quiz on Wednesday into Thursday for that. So you've got your instructions that are already up on the website. So hopefully you're looking at that, anticipating that. Tomorrow we'll have some review stuff going on. So I just want to make sure that you guys are in good shape for that. And then make sure that you submit things following the directions. Okay? All right, well, I hope that you use this opportunity the whole rest of the week here to spend some time seeking God, and then Friday, especially on Good Friday, when we think about what Jesus did for us and how much he loves us, and then going into Easter also with being able to celebrate his resurrection. I am praying for you, and I miss you so very much, and looking forward to at some point seeing you again, hopefully before the end of the school year. Let's all pray in agreement for that. All right, God bless you and have a great, wonderful day.